So up to last class, we have completed the concept of center of mass. We did conservation of momentum of center of mass. And the next topic is rotation. Let's start with the kinematics of rotational motion. Kinematics of rotational motion. Kinematics of rotational motion. Okay, when we start kinematics of rotational motion, let's start with, we will use few parameters that we have discussed in circular motion. We already discussed these parameters twice, one in circular motion, then another time in dynamics of circular motion during bending of rod and everything. Those parameters are theta, which is angular displacement. Theta is angular displacement. Then you have omega naught, which is initial angular velocity. Initial angular velocity. Then we have omega, which is final angular velocity. This is final angular velocity. Then you have alpha, which is angular acceleration. So you're already aware of all these relations. You know what is theta, you know what is omega naught, you know what is omega and alpha. Now we have to study motion with uniform angular acceleration. We need to do motion with uniform angular acceleration. Motion with uniform angular acceleration, which means motion if your alpha is constant. If your alpha is constant, then you have to calculate all equations of motion. If you remember, in uniformly accelerated motion, we take this condition that linear acceleration is constant. If acceleration is constant, then velocity is u plus at. Displacement is ut plus half at square. And v square minus u square is 2s. This is it. V is u plus at, s is ut plus half at square, and v square minus u square is 2s. These three equations we did in uniformly accelerated motion. Just corresponding to these equations, we can derive equations for uniform motion with uniform angular acceleration. See, we are just taking analog. Instead of v, I'm using omega. Instead of u, I'm using omega naught. Instead of a, I will use alpha, and time is time. So this is first equation. The method to derive is even same. The way we have derived these three equations, we can derive the similar equations with uniform angular acceleration. Or you can write your theta as it's omega naught t plus half alpha t square. That's second equation. We can derive even the third equation, which is omega square, omega naught square is twice of alpha theta. Instead of v, I'm writing omega. Instead of u, I'm using omega naught. Instead of a, we have alpha. Instead of s, we have theta. So that's omega square minus omega naught square, which is equal to twice of alpha theta. So these are the equations. The next is in NCERT, you are supposed to derive these equations. So to derive this equation, the first relation, omega is omega naught plus alpha t. If you remember the derivation of v is u plus at, you can just do this derivation, just have to put the analog. Like if you can remember v is u plus at, to derive this equation, we started with the equation of acceleration, that acceleration is dv by dt. In the same way, here, you will write angular acceleration alpha Angular acceleration alpha is rate of change of angular velocity, which is d omega over dt. You can multiply it with dt to the left hand side, and you will get alpha dt is d omega. So this d omega is small change in angular velocity in time dt. You need change in angular velocity from 0 to t. So this statement means d omega is change in angular velocity in time dt. So in a small interval of time dt, the change in angular velocity is d omega. This is it. But I need change in angular velocity in time 0 to t. I need change in angular velocity from 0 to t. So to calculate the change in 0 to t time, you can just integrate both the sides of this equation. Like this is alpha dt, this is d omega. You can integrate it from 0 to t. You can integrate it from omega naught to omega. See here, alpha is constant. You can take this alpha outside this integral sign. This is 0 to t dt. And this is d omega, omega naught to omega. Sania, what is the integral of this dt? Yes, Sania. Integration of dt. What is integral of dt? Integral of dt is t. What is d omega?
W.
Integral of d omega.
W.
Yeah. Limit is from omega naught to omega. So that's alpha. If I substitute limit, this is t minus 0. And this is omega minus omega naught. This is it.
Got it.
You got it. So that's the first equation. These equations are similar to the three equations of motion: v is u plus at, s is ut plus half at square, and v square minus u square is 2s. Even the method of derivation is same. Now let's derive third equation. Theta is omega naught t plus half alpha t square. To derive this equation, we start with the definition of angular velocity. Angular velocity omega is d theta over dt. This is omega, which is d theta over dt now. So omega dt is d theta. So what is d theta here? D theta is change in angular displacement in time dt. That's change in angular velocity in time dt. That is d theta. I need angular displacement in time 0 to t. I need angular displacement in time 0 to t. Now to calculate angular displacement in time 0 to t, just integrate on both the sides. D theta. And this is omega dt. The time is from 0 to t. When your time is 0, you can take that your displacement is 0. At time t, your displacement is some t. There is one problem with the right hand side of the integral. See, this omega is variable. T is variable. On the right hand side, you have two variables. You cannot integrate two variables simultaneously. You can at most integrate one variable at one time. So you have to write this omega as omega naught plus alpha. I'm repeating again. This right side of the equation have a problem. You have two variables. You cannot integrate two variables simultaneously. So to remove omega, I just substitute omega naught plus alpha t.
Sir, omega naught plus alpha t is constant.
Let's see, are they constant or not? Let's check. I'm just first substituting, then we'll see one by one which term is constant and which is variable. Because you can have one variable but not two different variables. Dt, it's 0 to t. So this is d theta. Limit is from 0 to theta. This is from 0 to t. If I multiply it here, this is omega naught dt plus alpha t dt. So this is integral of d theta. It's 0 to theta. It's 0 to t. It's omega naught dt plus 0 to t. It's alpha t dt. Now see, omega naught initial angular velocity is a constant term. Initial angular velocity omega naught is constant. Alpha angular acceleration is constant. So this is 0 to theta d theta. Omega naught is constant that I can take outside this integral. This is 0 to t dt plus alpha is a constant. You can take this constant outside this integral. It's 0 to t dt. Okay, so omega naught and alpha are constant that you can take outside, but t is a variable. So if you take these integral, this is in t only, this is in t only one variable in the right hand side. Is it clear? See, someone you were asking whether all these terms are constant. Omega naught is constant, alpha is constant, but not this t. Now, if I start integrating it, the integral of d theta is theta, it's 0 to theta. Omega naught is constant, integral of dt is t, limit is 0 to t. Alpha is constant, integral of t is t square by 2, limit is 0. So this is theta minus 0. This is omega naught, which is t minus 0, plus its half alpha, it's t square minus 0 square. So you can write this as theta is omega naught t plus half alpha t square. Okay, next take third equation. The third equation is omega square minus omega naught square is twice of alpha. So for this equation, you can start with the definition of angular acceleration. Angular acceleration alpha is d omega over dt, not with angular acceleration. D omega over dt. But the problem here is this equation doesn't have time. It's independent of time. But here you are getting time. So somehow you have to eliminate time from this equation. To eliminate time, you can do one thing. You can just multiply numerator and denominator by d theta. This d theta over dt can be written as omega. This d theta over dt is omega. So you can write your alpha as omega into d omega over d theta. You can multiply this d theta to the left hand side. Alpha d theta is omega d omega. So this d omega is change in angular velocity if angular displacement change by d theta. So I can integrate on both the sides. It's alpha d theta, integral of omega d omega. So initially your angular velocity is omega naught, your angular displacement is 0. Your final angular velocity is omega and your angular displacement is theta. You can take this alpha outside this integral. If I take this alpha outside this integral, we are just left with 0 to theta, d theta. And this is omega naught to omega. It's omega d omega. Next, we can integrate. The integral of d theta is theta. The limit is from 0 to theta. The integral of omega is omega square by 2. Limit is omega naught to omega. Next, you can write this alpha is theta minus 0. This is 1 by 2. It's omega square minus omega naught square. You can just multiply this 2 to the left hand side. So it's 2 alpha theta is omega square minus omega naught square. You can take this omega naught square to the left hand side. So it's omega naught square plus twice of alpha theta is omega square. So that's your third equation. So on application, so your theta is 400 radian. The time is 10 seconds. So the first one is straightforward, like theta is 400, omega naught is 0, half alpha into 10 square. Alpha into 100 by 2. It gets cancelled out. 4 into 2. 8 radian per second square. After this alpha, the second part, angular velocity after 20 seconds. You can use this equation. Omega is omega naught plus alpha t. Just keep on substituting the values. Omega naught is 0. Alpha we just have calculated 8. Time is 20 seconds. You need velocity after 20 seconds. So just put 20 here. So omega is 160 radian per second.
Yes, sir.
Let's do one more question on this concept. Just one more numerical. Remember one thing. One rotation is basically 2 pi radian. If a body takes one complete rotation, then the angle that it covers is radian. In SI unit, we don't measure angle in degree. We don't write 360 degree. Instead, we write 2 pi radian. Similarly, one revolution, the angle corresponding to one revolution is 2 pi radian. Next is one rotation we did, one revolution we did. The next is RPM. Sometimes you can get your omega in terms of RPM. RPM corresponds to its revolution per minute or rotation per minute. This RPM is not the SI unit. To convert this RPM into SI, just do one thing. One revolutions per minute means one revolution divided by 1 minute. See, neither revolution nor minute is the SI unit. So first convert revolution in terms of radian. Means it's 1 into 2 pi radian. Then convert minutes into seconds. That is 60 seconds. So your omega is pi by 30 radian per second. So if your velocity or angular velocity is given in revolutions per minute or in rotation per minute. So you cannot use this in revolution or in rotation. You must have to convert this in terms of radian per second. So multiply it with 2 pi and divide it by 60. Or just multiply it with 530. So you can say that one revolutions per minute is pi by 30 radian per second. You can use this direct relation, or you can multiply with 2 pi and divide with 60. One more thing. Say one rotation is 2 pi radians. You can write that one radian is 1 by 2 pi rotation. The next is just one last question on this concept. So the angular speed See, if I take the first one, this 1200. So this is omega naught, which is 1200 RPM, which is 1200 into 2 pi per minute divided by 60. It gets cancelled out, right? So it's 20. So your omega naught is 40 pi radian per second. Final is 3120.
Sir, why we took 60? It's 30, I think, no?
That you can either multiply it with pi by 30 or I'm using complete 2 pi by 60. So eventually if I divide it by 2, this will be pi by 30 only. Yes, Fazil, you are correct. Uh, Sania, you can even either multiply it with pi by 30, right? Or you can multiply it with 2 pi by 60. It's the same thing. I'm multiplying numerator and denominator by 2.
Okay.
So that's 40 pi radian per second. Yes, Fazil, your second part is correct. Good. Second, omega. Omega is 3120 RPM. So 3120 RPM basically means 3120 into 2 pi by 60. Yes, Noor, you're correct. Gets cancelled out. This gets cancelled out. 6 5 is 30, 6 is 12. So your omega comes out to be 2 to the 4, 5 to the 10, 104 pi radian per second. Your time is 16 seconds. So in the first part, you're supposed to calculate alpha. So you can use this equation. Omega is omega naught plus alpha t. So your omega is 104 pi. Your omega naught is 40 pi. Your alpha is unknown. Your time is 16 seconds. So you can write this as 104 pi minus 40 pi is 16 alpha. So this will be 64 pi will be 16 alpha. And alpha is basically it's 64 pi by 16. Your alpha comes out to be 4 pi radian per second square. So that is alpha, 4 pi radian per second square. Once you have alpha, you can calculate theta. And the second part, you're supposed to calculate theta, which is omega naught t plus half alpha t square. If I make all these substitutions, then your theta will be, theta is omega naught. Your omega naught, how much is omega naught? Omega naught is 40 pi. T is 16 plus half alpha. Alpha is 4 pi into 16 square. So this is 2. So theta is 640 pi plus 256 into 2. 256 into 2 is 512 pi. Am I correct? 16 square is 256. So 256 into 2 is 512, right?
Yes.
So if I add them up, this is 1, 6 and 500. This will be 1152 pi. So this is your angular displacement, which is in 1152 pi. But it's not asking to calculate the angular displacement. It's asking to calculate revolutions. Sania, what's the relation between number of revolutions and this thing, angular displacement?
1 revolution is equal to 2 pi radian.
Yes. So this much of radian, to convert radian into revolution, you will divide it by 2 pi.
Yeah.
You can write that 1 radian is 1 by 2 pi revolution.
Sir will not put the value of pi, like 22.
It gets cancelled out.
Okay.
So 1152 pi will be 1152 pi into 1 by 2 pi. So pi will cancel this pi. If I can divide it by 2, 2 5s are 10. 7 and 6. 5, 7, 6 revolutions. The next thing is dynamics of rotation. By the way, what is the difference between kinematics and dynamics?
Dynamics is with force, like including force, and kinematics without force.
That's true in straight line motion. Basically, kinematics means study of motion without considering its cause. When I say kinematics, that means you will study motion. Studying motion means you will study displacement, angular displacement in rotation, linear displacement in straight line motion. You will study linear velocity and angular velocity. You will study acceleration, but you will not study the cause of that velocity. Why is that accelerating coming? Why your body is moving with a certain velocity? You won't do those causes in kinematics. Kinematics, we just deal with motion. Whatever be the cause, once the body have moved, then you will calculate the velocity, the acceleration, the displacement of the body. But in dynamics particularly, we deal with the cause of motion. The cause of straight line motion is force, but the cause of rotation is torque. So dynamics means, so let's start. Let's write what dynamics means. Dynamics is branch of mechanics, sub-branch of mechanics. It's sub-branch of mechanics which deals with cause of motion. In straight line motion, the cause is force. Cause of translation, straight line motion is force. But the cause of rotation, if a body is rotating, then the cause is not force. The cause is torque. Cause of rotation is torque. So the laws of motion, in laws of motion, we studied the straight line motion of a body. So we studied force there. But now we have to study the cause of the rotation, why the body rotates. And the cause of rotation is torque. We'll start with torque. So if you want to rotate a body, you will apply torque to the body. Say if we talk about the fan, when fan rotates, then the motor of the fan applies some torque over the fan. Due to that torque, this fan rotates. If I'm rotating this pen, I'm applying some torque over the pen. The pen rotates due to this torque. And in any case, if you are rotating something, you're applying torque on that body. Now, what is torque? How to calculate torque? So the definition of torque is moment of force. Moment of force means you're applying force, but in a way that force gives rise to something which is rotating. So the rotation analog of force, that we write moment of force. When we write moment of force, that means force is generating something which can rotate. Moment of force about axis of rotation. Axis of rotation is torque. So the moment of force about the axis of rotation is torque. This is torque. So if a body is rotating, then the moment of this thing about the axis of rotation is torque. We will not derive the expression of torque. We will just define it. What is torque here? So to define torque, let's take a coordinate system. This is a coordinate system, XY coordinate system. This is the origin of coordinate system. And let's say this is a rod. I'm considering this point of the rod. This point is fixed at this point O. I call this fixed point O as the axis. To understand this diagram, see, This is the pen. I fix the pen at a point. This is my origin of my coordinate system. In the diagram, that is O point. This is the point, and I'm applying force over this point. So just tell me, is this point translating or rotating?
Translating.
Translation means straight line motion. Translation means it's
Rotating.
moving in a straight line. Translation means straight line. So this is the pen. I fix this pen at some point, and I call this point as origin. I'm applying some force over the pen. So due to this force, this pen is rotating. That means this force is providing torque to this pen. So this is that point P, and I'm applying some force over this point P, and say that force is so that's your coordinate system. This is your point O. I place a rod here. I take this point P over the rod. This rod is fixed at this point O. This is fixed. It cannot translate. If a body is fixed somewhere, like if your fan is fixed with the wall, the fan is fixed with the ceiling. So a fan cannot translate. It cannot move from one point to another. So if a body is fixed, it cannot translate. It can only rotate. So if I apply some force over this point P, let's say I apply force in this way. I'm applying this force. It's like I take this pen, see in the video, I take this pen, I fix this pen somewhere, that is my point O, and I'm applying some force over the pen. Then instead of translating, this fan is rotating. This pen is rotating. Rotation means due to my force, a torque is acting over the pen, and that torque is rotating this pen. Okay, can you tell me what's the net force over the pen? Applying a force, but this pen is not translating, it's rotating. Can you tell me the net force over the pen?
0.
Net force is 0. Because if some net force acts on the pen, then it will definitely move. If a body is not translating, it's not moving from one place to another. That means net force over the body is 0. So the net force over this pen is this case is 0. It's not translating. It's not going anywhere. The net force is 0.
So net force is 0, but torque is?
Yeah. Net force is 0, but torque is non-zero. The force that we are applying is providing a torque over it, but that net force is 0. So why the net force is 0? You're applying some force, but this pen is fixed to a support, to an origin. That origin is also applying a force over the pen. So the force that you apply get cancelled out with the force due to this support or origin. The net force is 0, but there is some torque acting over the pen, due to which this pen is rotating. Similar is the case with your fan. The fan is attached to the ceiling. It cannot move. The net force over the fan is 0. It's just rotating. That means a torque is acting over the fan, which is rotating this thing. Because if some net force act on the fan, then it will move. It will move from one point to another. It's not translating. That means net force is 0. It's rotating. That means some torque is acting over the fan. So this point P does not translate. It starts rotating in this way. It starts rotating in this way. It will complete a circle around this point. This is origin, and this is the point. This is my origin. And this P is point of application of force. Point of application of force. Point of application. So the separation between the origin and the point of application of force is R. This is R. The separation between them. So what is R? Position vector of point of application of force with respect to origin. That's all. This is the direction of R. Now, if this is R and this is F, so the angle between R and F is theta. Theta is the angle between R and F. Theta is the angle between R and F. Okay, can you just tell me how this rod is rotating? This is rotating in clockwise sense or in anti-clockwise sense?
Clockwise.
Anti-clockwise.
Anti-clockwise. This is rotating in anti-clockwise sense. So the torque acting on this coil or the torque acting on this rod, I'm writing it here. The torque on rod, I represent that torque by tau. That torque is the cross product of position vector and force. See, this is the definition of torque. This is how we define torque. I'm not deriving this expression. This can be derived in abstract mathematics, but we will not derive this expression. We will in fact use this expression. This is the definition. The way we never derived why speed is distance upon time, we just take that definition and then we derived other factors using that derivation, definition of velocity or speed. In the same way, I will not derive this expression that y torque is r cross f. This is our definition. We will use this definition. But using this definition, we will derive many other results. So that's torque, which is r cross f. If I open this cross product, then this torque comes out to be Rf sine theta. You remember cross product? R cross f is Rf sine theta. You can write this torque in one more form. This one formula, which is R cross f. You can do one more thing. What we can do is we can just extend this line. This is known as line of action of force, line of application of force. This is line of application of force. And this is the origin. So the perpendicular distance between this line of action of force or line of application of force and origin is this. This is the perpendicular distance between the axis of rotation and this line of action of force, R perpendicular. So here R perpendicular is perpendicular distance. It's perpendicular distance between axis of rotation and line of action of force. Physically, perpendicular distance means minimum distance. If I give you two lines, see the distance between these two lines is variable. It varies. If I ask you to calculate the minimum distance between these two lines, then you will drop a perpendicular. If I say calculate the minimum distance between this point and the line, or two lines, a point and the line, it keeps on changing, right? This is this distance, all are different. So if I ask you to calculate distance between a point and line, then you can have many distances. But if I ask you to calculate the minimum distance, then you will drop a perpendicular. You would say, yes, this perpendicular is the minimum distance, the point and the line. In the same way, this is the line. This is line of action of force. And this is the axis of rotation. This is your axis. The axis about which this rod is rotating. So the minimum distance between this axis and this line of action of force is R perpendicular. that we call perpendicular distance. Actually, this is minimum distance. It's minimum distance between axis of rotation and line of action of force. Between axis of rotation and line of action of force. This is our perpendicular. So if this angle is theta, I can say this angle is theta. Let's name this triangle, it's ONP. In triangle ONP. If I calculate sine theta in this triangle, sine theta is the perpendicular upon this hypotenuse. So sine theta is ON over OP. ON is R perpendicular, OP is R. So you can say that your R perpendicular is R sine theta. That's my equation number 2. So R perpendicular is R sine theta. The first equation is this, that torque is Rf sine theta. That's my first equation. I can do one thing. Instead of this R sine theta, I can substitute this 2. I can substitute 2 in 1. If I substitute 2 in 1, then this torque comes out to be R perpendicular. This is another formula for torque. You can calculate torque in 2 ways. Either you have R. Remember the difference between R and R perpendicular. R is the separation of point of application of force from the origin. Origin means your axis of rotation. While R perpendicular is the perpendicular distance between line of action of force and the axis rotation. Perpendicular distance means minimum distance. That's equation number 3. So two relations. You can either calculate your torque using Rf sine theta, or you can calculate your torque using R perpendicular F. Okay, now your torque is in anti-clockwise direction, right? Your body is rotating in anti-clockwise sense. But torque, the direction of torque is not clockwise or anti-clockwise. Your torque is basically an axial vector. It acts along the axis of rotation, so its direction could be outwards or inwards. It cannot be clockwise or anti-clockwise. Body is rotating anti-clockwise, but your torque can never be clockwise or anti-clockwise. Your torque is out along the axis of rotation always. So the direction of torque is along the axis of rotation given by right hand thumb. There are many methods to get the direction of torque. The one method is if you know the sense of rotation of body, if you know how the body is rotating, say here, the body is rotating anti-clockwise. Take your right hand, just keep your right hand over the screen like me. Keep your right hand, rotate, curl it anti-clockwise. Take your right hand and curl it along the sense of rotation of the body. If your body is rotating anti-clockwise, just curl your finger anti-clockwise. Where is your thumb moving? Into the screen or out of the screen?
Out of the screen.
Out of the screen, right? So the
Out
torque
of
is
the
acting out of the screen. This is one method to calculate torque. Just curl your finger along the sense of rotation. If your body is rotating anti-clockwise, just curl your finger anti-clockwise. If your body is rotating clockwise, then curl your finger clockwise. And this thumb will give the direction of torque. So your torque is acting in the outwards direction. So for torque, there's two methods basically. Curl your finger along the sense of rotation Thumb will give direction of torque. Okay, if this body is rotating in clockwise sense, then what's the direction of torque? You apply right hand thumb rule.
Into the screen.
Good. If it is rotating anti-clockwise, then your thumb is pointing inwards into the screen. That would be the direction of torque. Your torque would be inwards, not clockwise. Your torque would be inwards. And there is one convention which says that if the rotation is anti-clockwise, we take this as positive, means torque due to anti-clockwise rotation, or the torque which cause anti-clockwise rotation is positive, while we take clockwise rotation as negative. This convention is just due to the fact if the rotation is anti-clockwise, then your thumb is going outwards. Your thumb is along positive z-axis. That's why it's anti-clockwise rotation is positive. But if your rotation is negative, then your thumb is going inwards into the plane of the board. That's why we are considering this. And into the plane means negative z-axis. That's why we are considering that clockwise rotations are negative. This is one method. There's one more method which is based on cross product. I don't have much space. That is again right hand thumb rule. Using right hand thumb rule. Using a right hand thumb rule. So this is your torque tau, which is R cross F. This is your torque R cross F. So the next right hand thumb rule says, place your finger in the direction of first vector, that means R. Place your finger along R and curl it towards F. Curl it towards F. Thumb will give direction of torque. Thumb will give you the direction of torque. So this is the direction of R. So take your right hand, place your finger along R. This is the direction of R. This is R. So just take your right hand, place your finger along R and curl it towards F in this way. Where is your thumb pointing?
Out.
Yes, thumb is pointing out of the screen, right? Noor,
Yes.
Sania,
Yes, sir.
is it going
Yes.
outwards? Place your finger along R
Yes.
and just curl it towards F. Thumb is pointing outwards. So it's your choice. You can use any of the method, but you should at least know both of them. You can get the direction of torque using that circular path. Just take the sense of rotation, curl your finger along the sense of rotation, and this thumb will give the direction of torque. Or for the direction of torque, you can use this right hand thumb rule. Place your finger along R and curl it towards it. The next is the SI unit of torque. SI unit you can easily predict. Torque is R cross F. So this R is in meter, force is in Newton. So SI unit is simply Newton meter. What about the CGS? Noor?
Yes, 9 centimeter.
9 centimeter. That's the CGS unit. Okay, just note it down. Then we'll do some numericals on torque. A single numerical that will teach you how to calculate torque in a problem. Remember one thing. If line of action of force is passing through axis of rotation, then torque is 0. It means this is x-axis, this is y-axis, this is the axis of rotation. Yes, Fazil? No issues. And this is the direction in which you are applying force. So see, this is the axis of rotation. This is line of action of force. If I yes. So this is the line of action of force and this is axis of rotation. Your line of action of force is passing through the axis of rotation. Can you tell me how much is the perpendicular distance? What's the minimum distance between force and axis? It's simple. If a line cross a point, then what is the distance between that line and point? Sania?
0.
0.
Minimum distance is 0. So if your line of force pass through the axis of rotation, then your R perpendicular is 0. That means your torque will be 0. Remember this thing. You will need this concept in many numericals. Okay, the statement that I have written here is basically, if I take this pen, I fix this pen to this axis and I start pulling this pen outwards. Will this pen rotate?
No, sir.
No.
I take this pen. Yes, I take this pen. I fixed it over somewhere and I'm pulling this pen in this way. This pen will never rotate, but if I push in this way, then it can rotate. Basically, when I'm pulling this pen, the line of action of force is basically passing through this axis of rotation. When line of action of force passes through the axis of rotation, then perpendicular distance is 0. And when perpendicular distance is 0, that means your torque is 0. See, all questions that on torque that you will get in NCERT involved calculations that you will do in this numerical. If you can calculate torque in this numerical, then you will not stuck in any calculation of torque. So this is my rod. I fixed that this rod at point O. This point O is the origin. That's my axis, not origin. My axis is passing through this point. I take 2 points, one point P1, another P2. This separation is, this much is R1. Let's do it one by one. Over this point P1, I'm applying one force in this direction. This is force F1. This is perpendicular to R. You're supposed to calculate torque in this case. We will use both the relations, R cross F as well as RF sine theta. So, method 1. This numerical will teach you how to calculate torque. Method 1. This one, torque is RF sine theta. Now, if I apply this method, how much is R1? R is the separation between the origin and the point. The separation between the origin and the point is R1. The force which is applied at point P is F1. Angle between R1 and F is sine 90. So torque at point 1, tau 1 is R1 F1. This is method 1. The next is method 2. You can even calculate this torque using R perpendicular F. How much is R perpendicular? See, this is line of action of force. This is axis of rotation. I drop a perpendicular from axis of rotation to the line of action of force. And that perpendicular is equal to R1. So if I substitute all values, F is equal to F1. If I substitute all values here, then your tau is R1 F1. So you can use both the methods, you will get the same answer. That's part 1 of the question. Let's do one more part. Let's take the same rod, but now applying force in this way. Like this is the axis. Second part. all questions on torque that you will get in NCERT will use, I'm doing 3 cases, will involve any one of the 3 cases. And applying force in this way. This is F2. This is R2. Let's first start method 1. Method 1 says torque is Rf sine theta. What is R? The separation between O and the point of application of force. So this separation is your R. So your R is equal to R2 now. F is basically force F2. What is the angle between F2 and R2?
0.
See,
0.
R2 and F2 are acting in same direction signs. So your torque comes out to be 0. No torque is acting on it. If I use method 2, for method 2, I need this expression R perpendicular F. For R perpendicular, just stretch this line of action of force, extend this line of action of force till it passes through the axis of rotation. When it passes through the axis of rotation, R perpendicular is 0. Right? Because if line of action of force passes through the axis of rotation, then perpendicular distance is 0. Your R perpendicular is 0. Your torque is. So you can use any of the method. You can either use RF sine theta or you can use R perpendicular. Now I'm giving numerical values. Huh? So this is third. This is the origin. This is P3 over P3. This separation is say 10 meter. Applying a force in this way. This angle is 120 degree. Your force is 10 Newton. Calculate torque at P3 using both methods. Sine 120 degree is root 3 by 2 and sine 60 is again root 3 by 2. Okay, let's do it. See, first of all, the angle that you're using 120 degree. Yeah?
Yes, sir.
See,
Yes, sir.
this is R, right? The separation between the origin and the point. But see, the angle between the R and F is not this one. This is the angle. When we take vectors, we take angle between the arrows. So if I take this as vector R and I say this is vector F, then the angle between the vectors is this, not this one. So in vectors, the angle is always in between arrows. So this is the direction of first arrow. This is the direction of second arrow. The angle between both the arrows is this one, not this one.
60 degree.
So the angle is 60 degrees. The first mistake, okay? So if I use method 1, then torque is Rf sine theta. How much is R? R is 10. How much is F? It's 10 sine 60. So your torque is 100 into root 3 by 2. So torque comes out to be 50 root 3. Now that was method 1. You have also use method 2 also. For R perpendicular, let's draw perpendicular first. So this is it. This is point O. And this is the line of action of force, right? Extend your line of action of force. You know that this angle is 60 degree. And draw perpendicular from this origin to this line. This is O. This is P. How much is this? This is 10 meter. This is our perpendicular. If this is 60, then this is vertically opposite angle. This should be 60 degree. This is PON. In triangle PNO, you can write sine 60 as perpendicular, which is R perpendicular, divided by base, which is 10. So your R perpendicular would be 10 sine 60. It's root 3 by 2. It gets cancelled out. That's your R perpendicular. So your R perpendicular is 5 root 3 meter basically. So if you have R perpendicular, you can calculate torque. That torque is R perpendicular into F. R perpendicular is 5 root 3 into force, which is 10. So your torque is 50 root 3. After this numerical, you can get few conceptual questions on this. The first question is why handle of door are provided at extreme end. Why the handles of a door are provided at the extreme end. The reason is your torque is R perpendicular into F. Your torque is directly proportional to R perpendicular. So for a given force, just tell me, the door translates or rotates?
Rotates.
Rotates.
So for a given force, your torque is directly proportional to R perpendicular. The greater the value of R perpendicular, greater would be your torque. So when a gate rotates, basically this is the point at which the gate is attached to the wall, and then if you push it, it rotates in this way. This is how a door works, right? So it rotates about the axis which is passing through the wall. So if you apply handles at this extreme end, that means you are making R perpendicular to be maximum. Because if your R perpendicular is maximum, then your torque would be maximum. Since tau is proportional to R perpendicular, if R perpendicular is maximum, then torque is maximum. So just to maximize your torque for a given force, we provide handles at the extreme end of the door. Just to maximize your force, your torque, we provide handles at the extreme end of the door. This, due to the similar reason, wrench with long arm is used. So this is wrench which is used to open bolt. If you have a wrench, usually a wrench having a long arm is used so that R perpendicular is maximum and torque is maximum. So if you get conceptual questions like this on door or on wrench, the answer is you have to write this equation. You say that torque is proportional to R perpendicular. If R perpendicular is maximum, then your torque is maximum. That's the reason why the handles are provided at the extreme end of the door and wrench with a very long arm is used. The next topic is angular momentum. Okay, just like torque, this angular momentum is rotational analog of linear momentum. See, in straight line motion, in translational motion, we use linear momentum, which basically gives the amount of motion in a body. In rotation, instead of linear momentum, we use angular momentum. So the definition is similar. It's moment of linear momentum about axis of rotation. So the moment of linear momentum about the axis of rotation is known as angular momentum. The calculations of angular momentum are exactly same as that of torque. The only difference is instead of torque, we are using momentum. Instead of force, we are using momentum. So this is your body. This is fixed over this pointer. Instead of force, this body have a momentum. This is the direction of momentum of the body. P. This is the position vector R. This angle is theta. So angular momentum about O angular momentum about O, L is R cross P. If you open this cross product, you will get that L is RP sine theta. Same thing. You can even write this expression in terms of perpendicular distance. That's the line of, this is line of linear momentum. Line of linear momentum. And this is the axis. So the perpendicular distance is this R perpendicular. You can write this like previous calculation that R perpendicular is R sine theta. So your L will be R perpendicular into it. Just like torque, this is an axial vector. Its direction is along the axis of rotation. Direction is along the axis of rotation. So L is R perpendicular into it. The SI unit is its distance into momentum. So it's kg meter per second multiplied by meter. So it's basically kg meter square per second. Okay, solve this question. A body of mass m calculate its angular momentum. So this is your circular track. The mass of the body is m. The radius of the track is r. Body is moving with a velocity v. It's a very easy calculation. First calculate momentum, decide the direction of momentum, and then solve rp sine theta. It's hardly 3-step calculation. It's easy. Mass m, velocity v, so its momentum is mv, right? This is position vector r. This is origin. The axis is passing through the origin. The angle is 90 degrees. So L is rp sine theta. So r is radius of the circle. P is mv. Angle between them is 90 degrees. So this is mv. Okay. So if a body of mass m is revolving in a circle of radius r with a velocity v, then its angular momentum is mv.
Okay, sir.
Just note it down.
Done, sir.
Okay. Next, Newton's second law. For rotation, the Newton's second law is instead of force, we use torque, and instead of momentum, we use angular momentum. So your torque is dl over dt. If you want, you can prove it. It's a two-line proof. Say your L is r cross p. I can differentiate this equation with respect to time. When I differentiate this with respect to time, this is dl over dt. This is r is constant cross dp over dt. You can write your dp over dt is f. So yours dl over dt comes out to be r cross f. And what is r cross f? Torque. This is Newton's second. That torque is rate of change of angular momentum. Torque is dA over dt.